Hey, do you guys know what trees eat for breakfast? According to my sources, what trees eat for breakfast is oatmeal.
Come on now, dog. Come on, man.
But yeah, today we're going to start day one. We're going to get a nice introduction as to, what the birth of linear algebra was. Some theoretical, in fact, concepts that we need to have down pat so that we can understand the stuff that's to come. All right, here we go. Okay, folks, so let's talk about an equation of the form ax plus by equals c. All right, that would be an example of a linear equation. Of course, that's just one form of it. This would be the standard form of a linear equation. Other forms exist, obviously. I know one of the most popular forms of the line is slope-intercept form. When it comes to systems, it's sometimes more helpful to have the equations written in standard form. That way, it helps us to construct our matrices and what have you. With what I've written out, it's all purely notation, right? There are no explicit numbers in there. So just to make the distinction between the constants and the variables that are involved in here, we would say that the equation is linear in the variables x and y. Okay, and by saying that, it should be clear that x and y are variables, and we can assume that a, b, and c are constants or real numbers. And the graph of a linear equation, as you might expect, is a line. And I have an example of the graph of a linear equation. Really, it's just an excuse for me to put in a Watt meme, but Watt and linear equation. And here we have a line, and the equation that they actually are modeling here is y equals mx plus b. But there would be a way from going between y equals mx plus b and ax plus by equals c. All right, there's always going to be a way to do that. So yeah, this is the very well, I'll call it the germ of the beginning for linear algebra. All right, it's all born from the study of lines, in particular when we start putting more than one line in the same coordinate plane. But before we discuss those sorts of scenarios, I do want to inform you as to what makes an equation linear, because as you'll see, there'll be more and more variables inserted into that standard form equation, yet it still will be considered a linear equation. So you're not just confined to the variables x and y. We can have more in there, provided that the variables satisfy a certain criterion. So it says here, no matter how many variables are present in an equation, if none of them have powers different from 1, okay, that's key there, are not multiplied to other variables, and are not contained inside functions such as logs, trig functions like sine and cosine and tangent, exponentials, etc., then we would consider the equation a linear equation. All right, so things that are bad in terms of the equation not being linear would be situations where a variable has a power different from 1, or if we're multiplying 2 or more variables together, or if we see a variable contained inside of a function, okay, like the natural log or log base 2 or something like that, or even the square root. So with that said, I'm going to get generic here and define a linear equation in n variables. All right, and here's how I typically denote this. I use some subscript notation. I'm going to write a sub 1 times x sub 1. And I'll indicate what each of those are in just a second. And to this, I'm going to add another term of this form, a sub 2, x sub 2. To that, I'll add a sub 3, x sub 3. And we're supposed to have n variables in here, so there are going to be n terms. And since we're not really sure what the value of n is, to be as generic as possible, I'm going to add what's called an ellipses, and then another plus sign with a sub n times x sub n. And I'm going to set the sum of these terms equal to b. Now, each one of these a subscripts, I'll make a little note here, each a sub I is a real number, i.e., their coefficients. Okay? And then each x sub I is a variable. So we could technically say that this is a linear equation in the variables x sub 1 through x sub n. Now b is a constant. In other words, it's also a real number. Okay, but it's not a coefficient because it's not in front of a variable, right? So I would, consider that, or I'll basically be saying numbers that are on the right-hand side like that they're constants. Now, there's kind of a special case of a linear equation in n variables, and that has to do with a particular value of the constant term b. So we're now going to look at what's called a homogeneous linear equation in n variables. Now, the left-hand side of what we just wrote out will remain the same. So I'll still have those terms a sub 1, x sub 1, plus a sub 2, x sub 2, so on and so forth, all the way down until we get to a sub n, x sub n. But a homogeneous linear equation has a particular value of b on the right-hand side, and that particular value is the number 0. Okay, so anytime we're setting, our sum of terms equal to 0 in a linear equation, that makes the equation homogeneous. But either way, once you start mixing two or more of these so-called linear equations together, you form what's called a system of linear equations, or linear system for short. So these will be collections of linear equations, typically two or more, and the number of variables will really depend. So in some cases we might have 2 equations and 2 unknowns. In some cases we might have 2 equations with 4 unknowns. All right, so we got to open ourselves to situations such as the latter one. But I'll give you some quick and easy examples just to show you that it is something that we've probably worked with in the past. So an example of a linear system here could be something like 5x plus 2y equals 10, and 2x plus 5y equals 8. So something as basic as that. And of course, you can indicate that you're considering both of these at the same time, with half set of braces, just kind of enveloping them, if you will. So this would be an example of a linear system, particularly one that has 2 equations and 2 unknowns. And you'll notice that both equations are written in the standard form. But it doesn't have to be confined to anything basic like that, to be quite honest with you. You might have 3 equations where one is not in standard form. So say something like y equals 3x minus 17. And there might be a second equation where you have simply x is equal to 4. And then you might have another equation where you've got 2x plus z is equal to 0. So there's lots of different ways of mixing in equations with each other. But when it comes to solving a system, in our textbook or through Wiley Plus, obviously those equations will be provided to you, but they could be provided to you in a variety of formats. Don't always expect the system to come in standard format. It could come in y equals mx plus b, or a mixture of the two. But when we go to solve them, that just might require an extra step for putting them all in standard form and going from there. So, what is all this alluding to? Why linear algebra? Well, linear algebra really helps us to examine whether or not a system will have a solution and also helps us to address how many solutions a system will have. Okay, as you're probably aware, some systems, might have many solutions, whereas you might have a system with no solution whatsoever. And it's those concepts that really form the foundation of linear algebra. So it says here, one major aspect of linear algebra is examining the number of solutions to a linear system, as well as the techniques and processes for finding them, and also, their implications, a lot of the times geometric implications, and there are going to be some theoretical ones as well. So it probably is a good idea to define what a solution is, first of all. A solution of a linear system consists of values for the variables, okay, that are solutions to each equation, okay, and that's key there, all right? When we find a solution to a system, we have to make sure that it works in all of the equations that were provided to us to begin with, all right? And to solve a linear system means to find the complete solution set to the linear system. All right, and basically what that means is we want to find all the values of the variables that make the equations true. So with that, I want to provide some notation somewhere in this blank spot here. I'm going to call this solution notation. And this will be the case where we have a system with n unknowns. So let's say that we found the value of the first unknown, x sub 1, and generically speaking, I'm going to call its value s sub 1. So I'm writing out some parentheses, and it's basically going to look like an ordered pair, but just more generalized, because we're to assume n variables. So let's assume the first variable solution is s sub 1, so that would start out this ordered pair. The second variable solution is s sub 2, and let's go all the way down to the nth variable solution, which I'll call s sub n. And a solution such as this must satisfy all the equations in the system. So if we're saying that this is a solution, it must satisfy all equations in the system. Now, the notation here actually does have proper term or proper terminology. This is often referred to as an ordered n-tuple. When it's just two variables, we could call that an ordered pair or an ordered two-tuple. If it's got three unknowns and there's a solution for each of them, it would be an ordered triple or an ordered three-tuple. But of course, we start running out of those words like quadruple, quintuple, heptuple, and so on and so forth. So it's a little easier to refer to a solution of this type of format as an n-tuple.
A few moments later.
Linear Algebras, it's Mr. C here, and if you're wondering why I look so different than from the beginning of this video, that would be because most of the recording was done back during 2020, 2021, during the years of the pandemic. Ooh, glad those are over with. And if I was speaking a little bit slowly in my videos, I apologize about that, as I was on chemo during that time, but no longer on that, thankfully. Anyway, I realized that, in the 4 or 5 years that have gone by since that recording, that I probably took the long way to explain what linear algebra is all about. So I just wanted to clarify that in this short little clip here. Linear algebra is truly the study of linear systems, but also the objects that we use to study those linear systems, which would be matrices and vectors. And that really is it. And we'll be getting into those details with the videos that will come and follow after this one. But I want to thank you for your time for watching my video. I'm hoping to create a series of linear algebra videos to help everybody boss up in that subject, because I do think that it is one of the most important branches of mathematics, especially with the inception of AI. And to make my mark in this way and help you guys to better understand math and, dare I say, have fun with it, that would be definitely on my bucket list of items to achieve during my lifetime. So thank you for your support. If you haven't yet, please subscribe and hit the like button, ring the bell for notifications or whatever that is, and help support your homie from Detroit with his YouTube channel. And I look forward to helping you guys continue to boss up. And to close this video out, I want to share with you some fields in which you would apply linear algebra. So thanks again, and until next time, boss up and salute to you all.